Our problem is the function g is defined and differentiable on the closed interval -7 to 5 and satisfies g of 0 is equal to 5. The graph of y is equal to g prime of x, the derivative of g, consists of a semicircle and 3 line segments as shown in the figure above. The concepts we'll be using for this problem are the fundamental theorem of calculus, points of inflection, and relative maximums and minimums. The fundamental theorem of calculus states that given a function f is continuous on the closed interval a comma b, if there is a function g of x that is equal to the integral of f of t from a to x, then g prime of x is equal to f of x. Part 2 of the theorem states that the integral of f of x from a to b is equal to big F of b minus big F of a, where f is any antiderivative of small f. An inflection point is a point P on the curve y is equal to f of x if f is continuous there and the curve changes from concave upward to concave downward or from concave downward to concave upward at P. The concavity changes where f double prime of x changes signs. In order for there to be a maximum or minimum at c, c must be a critical number of a continuous function f. If f prime changes from positive to negative at c, then f has a local maximum at c. If f prime changes from negative to positive at c, then f has a local minimum at c. If f prime doesn't change signs at c, then f has no local maximum or minimum at c. For part A, we need to find g of 3 and g of -2. G of x is the area between g prime of x and the x-axis, according to the fundamental theorem of calculus. In order to find g of 3, we need to find the area from x equals 0 to x equals 3. This is the right half of the semicircle and part of the triangle. The equation for a quarter of a circle is 1/4 pi radius squared, and the area for a triangle is 1/2 base times height. The radius of the circle is 2, the base of the triangle is 1, and the height of the triangle is 3. When we plug these numbers into our equations, we get an area of pi plus 3/2. Now we have to add this to the initial condition, g of 0 is equal to 5, because the integral of g prime of x from 0 to 3 is equal to g of 3 minus g of 0. And we need to cancel out the negative g of 0 in order to end up with g of 3. We end up with the answer pi plus 13/2. In order to find g of 2, we must find the area between the graph and the x-axis from 0 to -2 and multiply it by -1, because in order to find g of -2, we need to find the integral from -2 to 0, but we have the integral from 0 to -2. The value we get is -pi. After adding the initial condition to this value, we get g of -2 is equal to 5 minus pi. For part B, we are asked to find the x-coordinate of each point of inflection of the graph y is equal to g of x on the interval -7 is less than x, which is less than 5, and explain our reasoning. Remember that points of inflection of the graph y is equal to g of x are found where g double prime of x changes signs, or where g prime of x changes from increasing to decreasing, or vice versa. These points are found at x equals 0, 2, and 3. For part C, we are given the function f is defined by h of x is equal to g of x minus 1/2 x squared. We are asked to find the x-coordinate of each critical point of h, where -7 is less than x, which is less than 5, and classify each critical point as a location of a relative maximum, relative minimum, or neither. In order to find the critical points of h, we need to take the derivative of h. We get h prime of x is equal to g prime of x minus x. We set h prime of x equal to 0 and end up with g prime of x is equal to x. So there are critical points where the graph of g prime of x intersects the graph of y is equal to x. By looking at the graph, we can determine that one critical point is at 3, 3. This is neither a maximum nor a minimum because the slope is positive both before and after x equals 3. There is another critical point on the right half of the semicircle. The equation of the circle is x squared plus y squared is equal to 4. We are looking for the places where y is equal to x, so we can substitute x for y. When we solve the equation for x, we get rad 2 for x. H prime of x is positive before x equals rad 2 and negative after x equals rad 2, because g prime of x is greater than y is equal to x before x equals rad 2, and smaller than y is equal to x after x equals rad 2. So there is a relative maximum at x equals rad 2.
at each top.